All right, ladies and gentlemen, we are going to look at that summative and try and figure out how to solve those three parts to the problems. So if we take a look at the first part, it is asking us to look at the reaction and determine the Gibbs free energy, which means that we're trying to find our delta G, which also means we need a balanced equation. We need to find delta S, we need to find delta H, and then we're going to have to put it in significant figures and make sure that we have the correct units on at the very end. So to start, we're going to look at our balanced equation. If we look at our reactant side, we know that we have two C's in our reactant side, which means our product side also needs two C's, which is why we put that 2 in front as our coefficient. If we look at our reactant side, we also know that we have 6 H's from that first ethane molecule, which means that we need 6 H's on the right side, which means we have to put a 3 in front of H2O to make 6 total H's on the right side, our product side. Now if we look at those product side, we can see that we have 2 times 2, which is 4, plus 3 oxygens, so you're making 7 oxygens on the right side. If we look on a reactant side, we have 1 oxygen plus 2 makes 3. So if we want to balance them out, we actually need 3 times our O2s to make 6 plus 1 to make 7. Now, if we are drawing out our molecules, we have CH3, which means our C has 3 H's bonded to it. Our next part is CH2, but remembering that carbon needs 4 bonds, our C's actually are bonded together. And then it becomes H2, which means 2 H's are coming off of our carbon. The last but not least, our oxygen is O and an H, but remembering carbon needs 4 bonds coming off of it, which means that we need oxygen and carbon to bond, which makes our molecule look like this. We then have 3 oxygens, and if we remember, oxygen has a double bond when it makes a reactant or makes an element. And then we make our carbon dioxide, which is C, which with 2 double bonds to 2 different oxygens. So our oxygens and our carbons all have 8 valence electrons. And then our water molecules look like this, with the H single bonded to an O, with another H single bonded to that same oxygen. Now that we have that, we are going to start with solving for our H value. So if we start for solving for H, delta H is equal to our absorbed minus our release, which remember is our reactants minus our product side. And if we do this, we first need to start with solving for that absorbed side. So we know that we have 5 times the amount of CH bonds, because if we look at that molecule from before, there were 5 times as many of those CH bonds. The next one we have is a C with a single bond to another C. After that, we know that we have an oxygen and a carbon bonded together with a single bond. And then in that same molecule, it also has an oxygen bonded to a hydrogen. That's one of the 2 reactants. That's all of what we need for that first one. Plus, we need 3 times as many O double bonded to another O molecules for our 3 sets of oxygen. Now that we have that, we can actually find our values. So if we find our first value of C bonded to H, we know that we're multiplying that value by 5. So 5 times 413 from that table for the enthalpy values. Plus, we find our C single bonded to a C, so we add 348. Plus our 358 for our CO bond, plus the 463 from the OH bond, and then finally our 3 times the 495 for our O double bond molecules. Now we're going to do some multiplication and addition, so we multiply 5 times 413 and we get 2,650. If we add our 348 plus our 358 plus our 463, we get 1,169 plus the 3 times 495, which is 1,485. Now, if we add all of these values together, we get 4,719 kilojoules per mole, because remember, enthalpy from the table has the units of kilojoules per mole. We now have our absorb side, so now we need to find our release side, which means that we need to multiply our carbon-oxygen double bonds. And if we look, carbon dioxide has 2 double bonds to an oxygen and carbon. And since we have 2 sets of those, we need 4 times the C double bond O molecules. Similar to water, which we have 3 sets of water, and each water has 2 OH bonds, which means we have a total of 6 OH bonds that we have to form. Now, if we find these values here, we know we would multiply 4 times the 799 for our CO bond, C double bond O, and we need to multiply 6 times the 463. Once we do some math here, we get 3,196 for the 4 times 799, and then we add it to the 2,778 for 6 times 463. When we add these values together, we get 5,974 kilojoules per mole for our release side. When solving for delta H, we do our absorbed minus release, which means we're doing 4,719 minus the 5,974. When we subtract these two values, we get a enthalpy value of negative 1,255 kilojoules per mole. Now, continuing, now that we have our delta H value, we're also going to solve for our delta S value. And we know that our delta S is our S of the products minus the S of the reactants. If we're solving for these, we'll start with our reactant side. And we know that the ethane molecule has an entropy value of 160.7 joules per mole Kelvin, plus 3 times the oxygen's value of 205.2. When we solve this, we multiply our 3 times 205.2, and then we add all of our values together to get a total of 776.3 joules per mole Kelvin. Now onto the product side. When we do this, we know that we multiply 2 times the value of carbon dioxide, which is 213.8, plus 3 times the value of our water, which is 188.8. When we multiply our values, we should have 427.6 plus 566.4. And when we add all those values together, we're going to get a total of 994.0 joules per mole Kelvin. To find our delta S, remember we have our S of our products minus the S of the reactants, so we are going to take our 994.0 joules per mole Kelvin minus the 776.3 joules per mole Kelvin. When we solve for this, our delta S value is 217.7 joules per mole Kelvin. Now our last variable that we're solving for is our delta G, and we know our delta G is equal to the delta H minus T delta S. If we solve for this, we know our delta H is a value of negative 1,255 kilojoules per mole. We also know our delta S value is 217.7 joules per mole Kelvin. And we know our last value of temperature is 298 Kelvin from the original problem. Now, if we take a look at those units again, just to make sure, our delta H and our delta S values have different energy units, which means that we need to convert one or the other. Remember, you have the choice of converting to kilojoules or converting to joules. I'm going to do from kilojoules to joules here, so we're going to set up our railroad tracks. We're going to put our negative 1,255 kilojoules per mole on our first column of our railroad tracks. We know we're trying to get rid of kilojoules, so we're going to put the 1 kilojoule on the bottom, and we know that the conversion factor for this is for every 1 kilojoule there are 1,000 joules. And when we solve for this, our units of kilojoules will cancel, and we should get a value of negative 1,255,000 joules per mole. Now we can set up our problem of delta G equals negative 1,255,000 joules per mole minus 298 Kelvin times 217.7 joules per mole Kelvin. We're going to multiply our temperature times our delta S value, and when we do that, we get a 64,874.6 joules per mole. And now when we solve for our delta G, it is negative 1,319,874.6 joules per mole. Now, I know what you're thinking. We got to convert to significant figures, so let's figure out those. If we look at our problem, all of our variables are going to have delta S and delta H have 4 significant figures, so let's convert to 4 significant figures. So we're going to round to negative 1,320,000 joules per mole, or if you want kilojoules per mole, it is negative 1,320 kilojoules per mole. Remember that decimal point after the 0 means that 0 counts for the significant figures. If there are any other questions, make sure you are contacting me to let me know if you don't understand anything that was going on.